So I'm going to go ahead and get into this. Okay, so I'm going to start this last part on 8.4. We're talking about what a remainder of a series is. So this is a theorem, 8.12, estimating series with positive terms. Okay, so let me explain what this theorem is saying. So basically, what you have is you have a continuous positive decreasing function that's represented by our series. And the first thing is you've got two series here. This is the series. This S, what this stands for, S is the sum of the convergent series. Okay, we got a series that we know converges. Okay, so that's what S represents. Okay, so let's just say we have a series, it converges, and we know what the sum is. That's what S is. Okay, then S of n is a part of that series. Okay, so S of n, you can think of this as a partial sum of that same convergent series. All right, so here's what you have. So tell me if this makes any sense. Okay, so first of all, what this is saying right here, we use this terminology R. R represents the remainder of the series. Okay, so this is what this is saying basically, is if you have the remainder is S minus S of n. Okay, so actually it's real simple. S is the total sum. So that would be the sum of the series all the way out to infinity, okay? Whereas S of n is some sort of a partial sum. So what the remainder is, that would just be like what's left over. If maybe you went out to 10 terms in the partial sum. The remainder would be whatever's left over. Does that make sense? Okay? So S is the big thing, the total sum. S of n is just a partial sum, just a little piece of that, okay? So that's what the remainder is. Well, okay, so we use this to establish bounds, and also we can use this to estimate, see how close we are with some series up to a certain number of terms. So actually, even though a lot of times it's very difficult to find the value of a convergent series, we might go out 10 terms and we might be very accurate, okay? So the idea is this remainder is always going to be bounded by this integral right here. And this integral is just going, this is really being like the rest of the series. So what you're doing is you're going to the end, so you're going to infinity, but you're beginning at some point like this, and you're representing that by a function. So that remainder is going to be less than the integral from n to infinity. And remember, this is not the series, this is an integral. Does that make any sense? Okay, that's going to be less than whatever that integral is from n to infinity. That's the remainder of that integral then. Okay, and then what you end up getting on this is you get this series right here, this series, and this is the sum. That would represent S right there. Okay, S would be the series of a sub k from k equals 1 to infinity. Well, that's going to be bounded by this partial sum. So that S of n is that partial sum, okay? And it's also going to be greater than this partial sum. And you got to think about this a little bit. This is the partial sum right here, plus whatever this integral is from n to infinity, and then it's going to be greater than n plus 1 to infinity like this. That's pretty abstract. It's not really that difficult to think about. So this is the exact value of the sum of the series. So that's going to be bounded by this integral, the partial sum plus that integral right there. Does that make any sense? I mean, think about that. That's just the partial sum. Maybe that goes out to 10 terms. And then this is the rest of it. But that's an integral of a function, so you would expect that to be a little larger than what that series is. Does that make it sense? Okay, just think of that as the part to n. Maybe it's the first 10 terms. Maybe that would be the integral from 10 to infinity. So it's got to be a little less than that. Now it's going to be greater than that partial sum plus that integral from n plus 1 to infinity like that. And that just means that's going to the next term like this. So you're going to expect this integral to be a little less than that integral. Does that make any sense? Remember, you got terms that are decreasing. So the way I look at this is, if you take out, if you're going from 10 to infinity, well, wouldn't the integral from 10 to infinity be bigger than the integral from 11 to infinity? Let's try that approach, okay? Because they're decreasing terms. So what you have is that sum that we're interested in is bounded by those two things, okay? Is there any question about that? Okay, got to think about that a little bit. So what we're going to be able to do is we're going to call this the upper bound, and we're going to call this the lower bound, and we'll be able to estimate the value of our series within, some degree of accuracy, okay? So what we're going to do, I'm going to do one example of this where you're doing a remainder. So what I'm doing down here is I'm giving this infinite series, okay? We're not going to find the sum, but we're going to estimate the sum. This is a convergent series, so we're going to find an upper bound. We're going to find how many terms that would ensure that the remainder is less than 10 to the negative 3. That means like 3 decimal points of accuracy. And then we're going to find the lower bound and upper bound. And then we're going to find the value of the series, what bounds it must lie within 10 terms of the series. Okay, so that's what we're after. Okay? Okay, so to begin with, and you can refer to this definition as we go this. What we're going to do is we're going to find a upper bound of the remainder of the term. So we're actually finding this thing right here, okay? So we're going to find what r sub n is equal to. Let me use a lowercase on that. Okay, so we got r sub n, okay? And then that's going to be equal to this integral right here. So we're going to go the integral from n to infinity. And let's see, what was that series on the previous page? That was 1 over k to the 8th, okay? So we're going to do this, and we're going to write that as x to the 8th. We're going to be using that function, because you're using that function, f of x, so we want to change that 1 over k to the 8th. Yeah, that's 1 over k to the 8th. Just going to make sure I'm doing the right thing here. Okay, and then we're going to make that 1 over x to the 8th. Now, this is an improper integral, so let's go ahead and do that. You should be able to do that okay. That's an improper integral. So if we have an improper integral, what do you change it to, usually? Like a limit, right? Okay, so we're going to say like a limit, and we're going to say from n goes to infinity, and let's see, let's use like, I guess we've been usually using the letter b on this. So I'm going to go b goes to infinity, and then we're going to do the integral from n to b. And I'm going to go ahead and write that as x to the negative 8 dx like that, and then we'll integrate that. So that should be a pretty straightforward integral to do, okay? So if we do that, we're going to have the limit as b goes to infinity, and then the antiderivative of that would be x to the negative 7 over negative 7, okay? Because you add 1 to the exponent, divide by the exponent, right? So that's going to be... I'm going to write that as negative 1 over 7 x to the 7th, and then we're going to evaluate from that to n to b. Okay, so that's a pretty straightforward integral. Okay, all right. One thing I'm going to do on this is, of course, you got an integral. You can do what with the negative 1/7? You got a limit. So what can you do? You can pull that out. Okay, if you choose to. It's just as well to just go ahead and take that out. So just take the negative 1/7 out. Then we're going to have limit b goes to infinity 1 over x to the 7th from n to b. Then we're going to evaluate that integral. Then we're going to do the limit as b goes to infinity. Okay, so let's go ahead and do that and see what we get then. Okay, so we're going to have negative 1/7. And let's see, if we evaluate the integral, the upper limit's going to be 1 over b to the 7th. Lower limit's going to be 1 over n to the 7th. And then we need to take the limit. I need to write in that I'm doing the limit b goes to infinity. Okay, everybody with me so far? Okay, that's a pretty straightforward improper integral that we've done. So now just replace be with infinity. So if you did that, you'd have negative 1/7. You can do this in your head. That you could think of that as infinity, like that. Okay, so where does this expression go to? 1 over infinity. That goes to 0, right? So what you're going to have is with this thing going to 0, you'll have this as a result. We'll have negative 1/7 times 0 minus 1 over n to the 7th. Then if you multiply that out, you have two negatives multiply out, so that should give you 1 over 7n to the 7th. And then you'll kind of see where I'm going with this a little bit in the next problem. Okay, so what that is that's an expression for the upper bound. Okay. Oh yeah, I just said that too. Didn't I say a negative times a negative is a positive? Okay. Yeah, okay, so we got that. All right, so we have that. Does that make sense what I've done? Okay, that remainder is bounded by this improper integral right here, n to infinity. So we have a mathematical expression. Now what n is in this problem, what does n represent? Really represents where this improper integral is going to start. So you can just think of that as the terms, however many terms you have. So what we're going to do is we're going to find how many terms are needed to ensure that the remainder is less than 10 to the negative 3. Okay? So what we're going to do then is we're going to take this remainder, this expression we got from the remainder, and we're going to set that less than 10 to the negative 3. Then we'll have an inequality. We can solve for n, and that would tell me how many terms we need to go out that will ensure that degree of accuracy in the remainder. Okay, so let's do that. So let's see. We have the remainder was 1 over 7n to the 7th, and we're going to set that less than 10 to the negative 3. Now I'm going to go ahead and write that as 1 over 10 to the 3rd, like that then. Okay, so what we need to do is we need to solve this inequality for n. There's two ways to do this. You can cross multiply when you're doing an inequality, but you got to be careful. I'm going to show this two ways. The first thing I'm going to do is to get rid of the 10 to the 3rd. I got a fraction, so I want to get rid of the 10 to the 3rd, so I'm going to multiply both sides by 10 to the 3rd. I also want to get rid of an n to the 7th. I don't care about the 7 so much, but you can get rid of the 7 if you want to. So let's just go ahead and do that. Multiply by 7 n to the 7th to get rid of that. Okay, so now let's kind of see what we have left over here. So what we're going to have left over here, it looks like, is 10 to the 3rd on this side, less than 7n to the 7th. And then what we're going to do is we're going to solve this for n. Okay, everybody following along what I'm doing okay? Okay? All right, now what do I need to do? I need to divide by 7. Okay, so from here I'm going to get 10 to the 3rd over 7 less than n to the 7th. Now what do you do to both sides of this inequality to change the n to the 7th into an n? You take a 7th root, right? Okay, so you're going to do like the 7th root of both sides then. Okay, so I need to do that. Okay, and if I do that, well, that's going to give n. That's going to tell you what n is greater than. And let's see, this will be the 7th root. And a 10 to the 3rd is 1,000 over 7. Okay, then I'm just going to take my calculator and I'm going to crunch that out. Okay, now like on a TI, you know, you don't do higher roots very often, but you can do this like this if you want to. You could go, like on a TI, you can go 7, then you can go math, and then you should have like X root key. You can do it this way if you want to. So that would be 7th root. Then you can put the 1,000 over 7 like that then. Okay, whoops, I don't need that parenthesis in there. I'm going to get an error if I do that. Okay, so let's see what that is then. Okay, so that gives about 2.03. N's got to be bigger than that. Okay, now keep in mind, what kind of number is n in a series? It's like natural number, 1, 2, 3, 4, right? So n is just numbers that you count by, like counting numbers. We call natural numbers. So it would make sense that if n has to be bigger than 2.03, then we would need it to be 3, okay? Not 2. 2 wouldn't quite be big enough to establish the 10 to the negative 3 value of that remainder. So what we'd get is we'd get n is equal to 3. Okay? What's that? Yeah, because it's a natural number. Yeah, and the thing about it is, see, since n has to be bigger than 2.03, 2's not big enough. Because where does it go from 2? It goes to 3, right? So you want to take that up to the next natural number when you do that. Okay? Okay, so that's kind of how that would work out. Okay, so what you're doing is you're seeing how many terms ensures that the remainder is less than 10 to the negative 3. And 10 to the negative 3 is 0.001. It's just got 3 decimals like that. So that means that if we go to n equals 3, we've got the accuracy of that remainder within 3 decimals. Okay, does that make any sense? Okay. All right, now we're going to go through and look at finding the upper and lower bound next and do that. Now what we need to do, I need to bring down my definition here so we can refer to this as we go through this, because we're going to do an upper bound and a lower bound when we do this. So I'm going to start by doing the lower bound that we call L of n. Okay, so what we do with this is your lower bound, this is what I was talking about, is this expression right there. Okay, this part is the lower bound, and then this part right here is the upper bound, like that. Okay, so we're going to do both find the upper and the lower bound on this. Okay, so what we do on this is, if we do this lower bound, we're going to do S of n plus the integral from n plus 1 to infinity of f of x dx. Okay, like that. Now we're going to leave S of n in there because we don't know S of n yet. What does S of n stand for? That's the partial sum, right? Okay, so and whereas S stood for what? The entire sum. Okay, whatever the value of that convergent series is. So when we set this up, I'm just going to leave S of n alone. Okay, then we're going to do the integral from n plus 1 to infinity. And then the function, remember we're doing the series of 1 over k to the 8th. So what do we want to do? We want to change that to x to the 8th. Okay, so we're going to use that function. We would expect the series to be less than the terms in that function, because that function has got infinite numbers of points, whereas the series is discrete points. Okay, so we want to go ahead and do this. This is an improper integral, so we want to just keep bringing down the S of n. So this is going to be limit, and we're going to change the infinity. What do we usually change infinity to? Like some letter, we've been doing b, so let's just keep doing that. So we got b goes to infinity like that. Okay, then we're going to do the integral from n plus 1 to b. I'm going to change that to b. Okay, then again, let's do that integral that we just did. Okay, except we're going to evaluate it in different limits here. Okay, so that's going to be S of n plus the limit, b goes to infinity, and let's see, the improper integral, or the antiderivative is going to be x to the negative 7 over negative 7. Then we're going to evaluate that from n plus 1 to infinity like that. Okay, everybody with me? Okay. Okay, now the improper integrals we're doing here are pretty simple. So what I'm going to do from here, I'll bring this up here. Still have S of n. That will be a part of our lower bound. You can bring the negative 1/7 out if you want to. That's what I'm going to do. So I'm going to have minus 1/7 times the limit as b goes to infinity. And then I'm going to go ahead and write that as 1 over x to the 7th. And we're going to evaluate from n plus 1 to b like that. And see where this leads us in. So this is S of n. I'm going to write that as minus 1/7. Then we can go ahead and evaluate our limits of integration. So you can plug in a b, then you can plug in the n plus 1. Then we still got to do the limit though. So I need to bring that limit down. Okay, so plug in the limits. You're going to have 1 over b to the 7th minus 1 over, that would be n plus 1 to the 7th like that. Okay, now when you do this limit, okay, next thing is when b goes to infinity, what is this term right here going to be that I highlighted? That goes to 0, right? Because that's really, what is it? It's 1 over infinity to the 7th. Okay, that's just 1 over infinity is going to 0. Okay, so when you do that limit, you're going to end up with s of n minus 1/7. That's going to go to 0, so you'll have minus 1 over n plus 1 to the 7th. And then we're going to write our final expression like this. So our result, let's write this like this. So our lower bound is, you got two negatives, make a positive, so it's 1 over 7 times n plus 1 to the 7th. Okay, so that is an expression for our lower bound like that then. Okay, so that's what we end up getting. What's that? Oh, I forgot my S of n, didn't I? I'm being a little sloppy there. Sorry about that. So yeah, we should have this. We should have lower bound is S of n minus 1 over 7 to the n plus 1 like that. Okay? So that's how that's going to go. Now what we can do is we're going to go ahead and find the upper bound, but we've already really kind of found that. So if you'll have to go back to the part A of the problem. So if you do your upper bound, which we'll say u sub n, well, here's your upper bound right here. That's the expression. So you say S of n, and we already did this improper integral. So if you look at part A, this is what you got in part A is this right here. So that's going to be 1 over 7 to the n plus 7. Okay, so that was what? 7, yeah, 1 over 7 to the n to the 7th. So what I'm doing on that is I already got that in part A, then we did that part right there in part C. So that's our upper and lower bound. Okay, all right, you guys follow what I'm doing. It's pretty abstract, but the mathematics, the calculus behind that, the improper integral is not that hard.
So the lower bound should be positive?
What's that?
The lower bound should be positive?
Oh, it is. Okay, that's the second time I've done that too. Negative times negative is positive. Right there, so we got that.
So usually
Okay, now I think I'm good.
So usually the upper, like the lower, go the same?
Yeah, and see the thing is, we already did this right here. This is the upper right here. So we already did S of n. See, we already did the integral into infinity. If you go back to part A in the problem, see, we already did that integral right there. Okay, so what that is that's the remainder. Okay, right there. So that's 1 over n to the 7th like that. So that's how I got that. We just already did the work on that. Okay, any other questions with anything? Okay, now let's put this all together. So we're going to put this all together and kind of wrap this up then. So what we're going to do is we're going to find an interval in which the value of the series must lie if you approximate it using 10 terms of the series. So we've got, and again what we have on this is we got the lower limit and we got the upper limit like that. Okay, so the lower limit, let's see what that was, what, S of n. What did I have on that? I had this, I'm just going to write this down. You don't have to write this down. I just want to write it down so I can refer to it. So that's what the lower limit was. Then the upper limit was S of n plus 1 over 7 n to the 7th. See, notice what's the only difference between the upper and lower limit? That's it. Okay, that changed to n plus 1. Now, does that make sense to you guys? This is something it's not that hard. You have to think about it a little bit. Is this right here is the next term in the series, so wouldn't this thing be smaller than this? Okay, another way to look at this is like this. If you have a bigger denominator, then this is a smaller expression than that, okay? Like if n was 1, that would be smaller than this, because that would be a bigger denominator. Does that make sense? Okay? Like for instance, here's a simple way to do this. 1/8 is less than 1/2, right? Because the numerators are the same, but that denominator is bigger, okay? This is, if you cross multiply this way, you get 2 less than 8, okay? So we know that that is smaller than that, so that is how you can make sense of how these upper and lower bound work then, okay? So what we're going to do then on part D is I want to go ahead and we're going to do, it says 10 terms, I think. So we're going to do S of n, or S of 10. Now, what does S of 10 mean, by the way? That's the sum of the first 10 terms. That's not the sum of the infinite series, but that's the first 10 terms. So what we're doing is we're going to do the series from, let's see, the series we're working on is k equals 1 to infinity, but now we're going to go 1 to 10. And then we do 1 over k to the 8th. Now let's write out the terms. I already did the calculation on the calculator, but I'll explain what you have to do. So let's see, what would the first term of this series be? Wouldn't that just be 1? 1 over 1 to the 8th. What's the next term in the series going to be? 1 over 2 to the 8th, right? Then you got a nice pattern. What's next? 1 over 3 to the 8th, and so forth like that. Then you're going to close off with 1 over 10 to the 8th like that. Okay? Now you could use a calculator to do that. And so what you could do on that, I went ahead and did this on the calculator. So I did that before class to make sure I had that. I think I wrote that down. Yeah, here we go. This is 1.004077346. Okay? And if you look at this convergent series, you kind of get an idea. What if we went all the way out to infinity? Any idea what that probably might be going to? Probably 1. Okay, that's just kind of my suspicion. Because see, we are already, when we did this, we were already kind of accuracy within 10 to the third. So that's what that's probably going to go to. Okay. Then we want to do the lower bound of 10. Well, the lower bound of 10, you just want to take this expression right here. So you want to do S of 10 plus 1 over 7. And then you want to replace that 10 with that n with 10. So you're going to get this. Okay. So see, we already got S of 10. S of 10 we calculated as 1.004077346. Then we could do plus 1 over, and see, this is going to be 7 times 11 to the 7th like that. Okay, so again, what I'm doing is I'm just plugging in n equals 10 there, and then we already got the partial sum right there. Okay, now let's see, I think I also went ahead and worked this out. And let's see, I wrote this down somewhere. Let me remember where I wrote it down. Here we go. Okay, so this is approximately 1.004077354. Okay, like that. And then the upper bound of 10 goes like this. So the upper bound formula is going to be like this. So we're going to do S of 10 plus 1 over 7, and again, replace the n with 10. So that's going to be 1 over 7 times 10 to the 7th. And that worked out to be about the same. It's just because my calculator doesn't go out any further. So it was almost the same thing, I think. Like that. I think they turned out to be the same. You can check my calculation if you want to. I did that before class. They turned out to be the same. Just the only reason is because my calculator only goes out to a certain number of decimal places like that. Yes?
So I have a question on the first decimal we get is the 1.004. Did you do this rule when you have find your A and your R and you did A?
You're talking about what, the partial sum, S of 10?
Yes, S of 10. Because there's a question like this in the homework. So did you do A multiplied by 1 minus R to the
What I did is I just did this. On my calculator, I just did 1 plus 1 over 2 to the 8th.
But there's another way when we do A multiplied by 1 minus R to the n divided by 1 minus R? When we add these together, or you just add the numbers in your calculator?
I just added the first 10 like that, okay? Now you're thinking of that as geometric series.
Yep.
Yes, so you could do that too if you wanted to.
Okay.
Yeah, you get the same thing, so you could use that same formula, A minus,
R to the n.
right, okay, n minus 1 over r. Okay, so we could do that. So anyway, that's what you have for your bounds. And then from that point, so what you're trying to do is find an interval that you must lie within. Now, you can go out further than that, but the idea is, if you look at the first 10 terms of this series, you're already getting fairly accurate. You would find that this is a convergent series that would go to 1. Okay, if you work that out. Okay, is there any questions about what I did there? Okay. Part of what we use this for, once we get into Chapter 9 and we start doing what we call Taylor polynomials and stuff like that, we start writing out terms. So we're going to use this idea a little bit in this. The other thing I want to do in 8.4 is just kind of summarize a few things. I just took some problems out of the book. The book tends to have, the exercises tend to have just some kind of definition problems and stuff like that. So let's look at a few things like this. This says, if we know that the limit of a sequence is 1, then what can you say about the sum of the series? Okay, well, one thing that we learned on this is, if the sequence of terms has a limit of 1, then that is going to mean that diverges. And that's what the divergence test was saying. If you go all the way back, I'm going to scroll back to where I had the divergence test here so I can just kind of remind you of what that is. So basically then what the convergence test did is what we looked at was, if the limit was not equal to 0 or does not exist, then we diverge. If the limit of the sequence was 0, then it's inconclusive. So when you're doing the divergence test, if you can establish that that limit is not 0 or doesn't exist, then it means that that's going to diverge. So that's what this question is basically saying then, okay? Okay, so it is necessary but not efficient that the sequence has a limit of 0 in order for the corresponding series to be convergent. And again, that's the divergence test. Now we said, like, if we did the limit of the sequence, if that goes to 0, we said it's inconclusive. Okay? So that's what just kind of is a review of what the divergence test is saying. So on divergence test, if it's not equal to 0, if the limit of the sequence is not equal to 0, what do you conclude? It diverges. Okay? Otherwise, if you get 0, then it's inconclusive, so you have to look at different tests to establish whether it converges or not. Okay, let's see if we know on this. Is it true that if the terms of a series of positive terms decrease to 0, then converges? Okay, so let's look at kind of an example on this. So let's look at, say for instance, you had this right here. We've looked at this before. Okay, do you guys, you're kind of learning this now, so you might not have everything memorized yet. Do you guys remember what this series right here is, 1 over k? We have a special name for this one. That's the harmonic series, right? Do you remember what we said about the harmonic series? That it diverges, okay? So the idea, like if you had a harmonic series, it would be 1 over a half plus a third and so forth like that. That is one of the ones that we said has been proven that it diverges, okay? So if you have a series of positive terms that decrease to 0, so you can tell that the nth term is going towards 0. So if you go way out here, you would have 1 over infinity going to 0. So does that mean it converges? The answer is no. Okay, so even though the last term of the series may be tending to 0, that doesn't mean that it's going to be a convergent series. Does that make sense? Okay, this is just one example. So the harmonic series would be a good example of that. There's others as well. Okay, so anyway, if you've got a series and the last term's going to 0, that does not mean that it's going to be convergent. Okay, that's one example. Okay. Okay, now the integral test. We learned a little bit about the integral test last time, and let me just kind of scroll back to where I had the definition of the integral test, just to kind of review that a little bit. When you do the integral test, generally you're going to use it when you have something that's pretty easy to integrate. And let's see, where did I have that? I have that in here somewhere. put the integral test. Yeah, here's the integral test right here. So let me just kind of remind you of what the integral test is saying. So basically what this was saying is you have a continuous function, positive decreasing, the terms are decreasing, so they're getting smaller, okay? Then what it said is if you compared the infinite series with the improper integral based on a function, then either both of these things are going to converge or both of them are going to diverge. So if you established that the improper integral converged, then what would be the result of the series? Converge also. If you established that the improper integral diverged, then what do you establish about the series? Diverges also. Okay, so that's what you're doing with an integral, with the integral test then. Okay, so what we would say then is, can the integral test be used to determine whether a series diverges? Yes, okay, it can. So, and what we learned is either the series and the integral, and that would be an improper integral. And then what did we say? We said the series and the improper integral, they both got to do the same thing. So we say they both converge or they're going to diverge. Okay, so that's the integral test. Generally, you're going to utilize that if I've given you the series, the expression, the function is something that's pretty easy to integrate. Okay, if it's a difficult thing to integrate, then you do some other kind of a test. Okay, so that's what we said there. Okay, now the next thing is do you guys remember what we called this series? It's got the letter P in it. That's a good clue. That's called a P series. Okay, so we have a P series. Okay, what we said on a P series, and a P series would be actually the problem that I was doing a little while ago where you were doing the integral of 1 over k to the 8th, or the series 1 over k to the 8th, that is a P series. And we said it converges when P is a certain value. What did you guys remember what we said on that? It's got to be greater than 1, okay? Then it says it diverges when P was less than or equal to 1. Okay, so see, this problem that we were working on previously was a P series, and it converged because 8 is greater than 1. So that was a P series. Okay, that would be the idea. Okay, so now we want to kind of look at, let's see, the remainder of the terms. I want to do one more here, and I'm not going to get into that number 8 very much. So the remainder of the infinite series, we usually just call that the error in approximating a convergent infinite series by a finite number of terms. So what we're kind of doing, like with that problem that we were doing with the remainder with this P series 1 over k to the 8th, is we were able to see up to 10 terms how close that was to the actual value. So that's kind of an error in approximating a convergent series. So whatever is left over is going to be the error in that approximate series. Okay, and let's see, the last thing, if a series of positive terms converges, does it follow that the remainder must decrease to 0? And the answer to that is yes. I'm not going to get too much in the into the theory behind that, because we're not going to really do anything with proofs and things of series. So what would happen on that is if a series of positive terms converges, then the remainder must decrease to 0. And the reason for that is you would think the error would go to 0. Okay, so basically if you do more and more terms in that remainder, that should go to 0 as well. Okay, all right, so that'll wrap up what we do in this